In class today, we are going to solve a very classic problem, and that is to consider a series reaction where A goes to B, which of course we've talked about and we've seen already this semester, and then B goes to C. And we want to solve this problem assuming that both reactions are elementary and these reaction rate constants, right? K1 is 0.06 inverse minutes, K2 is 0.04 inverse minutes. We know the initial concentration of A, the initial concentrations of B and C are both equal to 0. And so determine the concentration of A, B, and C as a function of time. A nice thing about this problem is that we are going to have an analytical solution. So we have A goes to B, goes to C, right? K1, K2. So how are we going to start this problem for an ideal batch reactor? Well, we know that dNi dt is equal to Ri times V. And of course, we have a constant volume batch reactor. So that gives us dCi dt is equal to Ri. So for each one of these species, we have to determine what the rate law is going to be. So let's do A first. So we have dNa dt then is equal to Ra. And can somebody come in and tell me what Ra is equal to? What's the rate law for species A?
Just minus K1 times Ca.
Yep, exactly. We have an elementary reaction that's equal to minus K1 times Ca. That's great. So minus K1 times Ca. All right, fine. So now let's do B, dNb dt. So what is, right, that's equal to Rb. So what is Rb equal to? So A was minus K1 Ca because it only participated in the first reaction, but B is going to take part in both reactions. It'll be formed in reaction 1 and consumed in reaction 2. So how do we capture that here in Rb? So what's the rate law for B?
Will it be negative K2 Cb plus K1 Cb?
Yes, that's right. And right, so we have, well, here it's K1 times Ca minus K2 times Cb, right? I think that you said Cb here as well. But yeah, it's the rate that B is formed, which is minus the rate that A is consumed, then minus the rate that B is consumed. And if that's an elementary reaction, that's just K2 times Cb. So then dCb dt then is just K1 Ca minus K2 times Cb. Great. And we know that dCc dt for this constant volume ideal batch reactor is then equal to Rc. So what's Rc equal to? So we know that it's formed through reaction 2, and that's the only reaction, and it has to be formed at the same overall rate that B is consumed. So what would that be?
K2 Cb.
Exactly, K2 times Cb. Good. So that means that dCc dt is equal to K2 times Cb. So now we have to go about solving these problems or solving these equations in this problem. Now, we could actually do Euler's method if we wanted to. And we would end up getting a perfectly acceptable answer. But we won't do that today. We won't, change these to deltas, pick a step size, and then do the whole voila, now, now the turkey's ready. Here's what the graph looks like. We can actually solve this analytically. So let's do that. Let's solve these equations one at a time. So we'll start at the top, right? So we have equation 1 equation 2, and equation 3. So let's look at equation 1. So we have dCA dt is equal to minus K1 times CA. So hopefully that looks familiar because we've actually solved this problem already multiple times. This is the same solution as when A goes to B from K1. And from A's perspective, it has no idea that the second reaction is even happening. So we're fine here. And if dCA dt is minus K1 times CA, we solved this already to find that CA was simply equal to CA0 times the exponent of minus K1 times time, right? And essentially we did that by dividing both sides of the equation by CA, multiplying by dt, and then integrating those two, right? And I believe that's in lecture 2. You can go back and find that solution in your notes. So we'll just take that as, yeah, we already know how to do this. All right, so let's move on and solve reaction or equation 2, where we're trying to solve for the concentration of B as a function of time. So we have dCB dt is then equal to K1 times CA, which we just solved for CA. So it's actually K1 times CA0 times the exponent of minus K1t minus K2 times CB. And of course, the problem is not as simple as just multiplying by dt and then integrating, because we also have B on that side of the equation. So we're going to have to use a trick to do that. And if you remember from differential equations, right, we are going to use the integrating factor method. And that factor for this particular problem is the exponent of K2 times time, okay? And what we do then when we use this integrating factor is that we are first going to add K2 to that side of the equation and then multiply everything by the exponent of K2 times t. And if we do that, that's dCB dt plus K2 times CB equals K1 CA0 times the exponent of minus K1 times time. And now I'll multiply all three of those terms by the exponent of K2 times t. So this becomes the exponent of K2t times dCB dt plus K2 CB times the exponent of K2 times t equals K1 times CA0 times the exponent of minus K1t times the exponent of K2 times t. Okay? And that's me just applying this concept of an integrating factor to both sides of this equation. And the reason that we do that, right, that we actually find an integrating factor, is to pick on this term here. Because that term, if you really look at it carefully, is just d over dt of CB times the exponent of K2 times t, right? And to prove that, if we just use the distributive property here, right, this would be the exponent of K2t times dCB dt, right? We're just taking the integral of the first term, plus CB times the differential of the exponent of K2 times t, which would be times K2 times the exponent of K2 times t. And that's exactly what we have here, okay? So all we've done is try to capture a term that that is one combined term that's inside of this time derivative, so we can multiply it by t, all right? So d over dt of CB exponent of K2 times t is just equal to the same thing that was on the right-hand side of the equation, right? So that's K1 times CA0 times the exponent. And we can combine these two terms, right? That those two things together can combine to simply be K2 minus K1 times time, right? Just using some rules of the logs. Now we can integrate those. So we're going to integrate this term from CB0 to the term that's actually inside of the integral. So we're going to integrate this from CB0, which we already know from the problem statement is 0, to the value of this at some time in the future, which is just itself, CB times the exponent of K2 times T. And then we're going to integrate the right-hand side of this equation from 0 to T. All right. And if we do that, we simply find that CB times the exponent of K2T is equal to K1 times CA0. Then when we integrate this term, right, we get 1 over that term. So that just is divided by K2 minus K1 times the exponent of K2 minus K1 times T integrated or evaluated from 0 to T. So we're getting there, right? So this is still CB times the exponent of K2 times T equals K1 CA0 over K2 minus K1 times now the exponent of K2 minus K1 times T minus 1, right? Because the exponent of 0 is just 1, okay? So now we can actually solve for CB. So we know that CB then, we're just going to divide both sides by the exponent of K2 times time. And if we do that, CB equals K1 times CA0 over K2 minus K1 times the exponent of K2 minus K1 times time minus 1 over the exponent of K2 times time, okay? And we can simplify that a little bit. And if we do that, CB then just equals K1 CA0 over K2 minus K1 times, so this K2 times T is going to cancel with that K2 times T. And that's simply going to leave us with the exponent of minus K1 times time. And then we're left with this minus 1 over the exponent term, which just becomes minus the exponent of minus K2 times time, okay? And hopefully this result makes some kind of sense. This is like the concentration of B should be related to the initial concentration of A and the rate constants. And this is sort of the contribution of reaction 1 and the contribution of reaction 2. So we did all that math, but I think that we end up with a term that makes sense, or at least an equation that makes some kind of sense. So now, from what we've done above, right, we have an equation for the concentration of A and the concentration of B. So the one that's missing here is solving this equation for the concentration of C versus time. And we know that's just K2 times CB. So doing that, right, that's then just equal to K2 times K1 CA0 over K2 minus K1 times the exponent of minus K1T minus the exponent of minus K2 times T. And even though it might not look like it on the face, this is a much easier equation to solve than the one that we did just a second ago, because we can just multiply by dt and integrate directly. So we can have d CC is equal to K2, K1, CA0 over K2 minus K1 times the exponent of minus K1 times time minus the exponent of minus K2 times time dt. And we can integrate this from the initial concentration of C, which we know is 0, to the concentration of C at an arbitrary time. And then we can integrate that side from 0 to time. And of course, this is a constant, so nothing's going to happen there. So this is just going to be about integrating those terms. And so that becomes the concentration of C is equal to K2 times K1 times CA0 over K2 minus K1, right? That's the constant, times, now we'll just integrate those. Well, that's just minus 1 over K1 times the exponent of minus K1t minus 1 over minus K2. So that's plus 1 over K2 times the exponent of minus K2t. And that's evaluated from 0 to t. Okay. And if we do that, the concentration of C just becomes equal to K2, K1, CA0 over K2 minus K1 times 1 minus the exponent of minus K1 times time divided by K1 minus 1 minus the exponent of minus K2 times time divided by K2. Okay. And you could stop here. The other thing that you could do is multiply through by K2 times K1. And I'm just going to do that because then it gets rid of these two values in the denominator. And if I do that, CC just becomes equal to CA0 over K2 minus K1 times K2 times 1 minus the exponent of minus K1 times time minus K1 times 1 minus the exponent of minus K2 times time. And close that parentheses and close that parentheses. So there we have our expression for the concentration of C. Now, after that, you might think, oh, we should have done Euler's method. That would have been easier. And actually, at this point, that might have been true because we did, 10 minutes of calculus and implementing this in a software package or doing Euler's method in Excel, we actually probably would have had the solution in just a couple of minutes. But it is good when we can to not use an estimate, to actually be able to solve a problem analytically and get an exact solution. So that's really good. Okay, so we didn't use any new math here. So hopefully all the math made sense to you guys as we step through the problem. The question then is, why did we do this, right? Well, one reason is to see what the product profile actually looks like. And so here is a typical product profile for a process like this, where A goes to B goes to C. And of course, A is constantly consumed. So the concentration of A drops steadily over time, and it has that exponential decay that we would have been familiar with from just a simple A goes to B type of reaction. But B, because the concentration is initially low, the reaction rate for B to C is also very low. So what you have is this emergence of B, and it peaks at a point where the rate of formation of B and the rate of reaction of B are exactly the same, right? So that would be right at the very top. And then you start to consume B at a faster rate than A. And then C is just constantly formed over time, initially slowly, and then the rate picks up over time. And hopefully this makes a little bit of sense to you guys. So in a plot like this, we often want to do this because B is a wanted product and B to C is some unwanted side reaction that happens in our process, okay? And if we wanted to, we could figure out at what time we reach this optimal amount of B, okay? Or if I were to think about this in a mathematical way, we could figure out where dCB dt is equal to 0, right? This will give us the optimal concentration, or the maximum, maybe is a better way to say this. We'll get the maximum concentration of B. And if B is our desired product, often that is our design point, right? Let's make as much B as we possibly can. Well, the nice thing about this is that if we want to find where dCB dt is equal to 0, we already have this from our mole balance, right? This is the left-hand side, or the result of the left-hand side of our mole balance. So we know that dCB dt equals K1 times Ca minus K2 times Cb. And we just have to find where that's equal to 0. Well, that means 0 equals K1 times Ca0 times the exponent of minus K1 times time has to equal K1 times K2 times Ca0 times K2 minus K1 times the exponent of minus K1t minus the exponent of minus K2t, okay? And the first thing I can do is realize that, well, K1s will cancel and the Ca0s are going to cancel. And the thing that I really want to find here is time, right? I want to find the time where Cb is maximized and then plug it into all these other equations. So to do that, I want to get time on the same side of both. I want to get time on the same side of both equations. So I'm going to actually divide both sides here by the exponent of minus K1 times time. Okay. And if I do that from here, right, you find that 1 is going to equal K2, right, what's left over here, K2 over K2 minus K1 times the exponent of minus K1t minus the exponent of minus K2 times t divided by the exponent of minus K1t. And this works out kind of nicely because this is going to be 1. So that means that 1 equals K2 over K2 minus K1 times 1 minus the exponent of K1 minus K2 times t. Okay. Sorry, that's equals, not minus, right? 1 equals K2 over K2 minus K1 times 1 minus the exponent. And from here, we can actually solve for time, right? So K2 minus K1 over K2 equals 1 minus the exponent of K1 minus K2 times time. And we can then sort of rearrange this equation, right? And the exponent of K1 minus K2 times time equals 1 minus K2 minus K1 over K2, right? I just sort of flipped sides here for those two. And I'm going to make this one just K2 over K2 to give them a common denominator over K2. And if I do that, right, this side of the equation just becomes K2 minus K1 over K2, or this and that K2 will cancel, and this minus makes that plus. So that just becomes K1 over K2. Right? So that gives us the exponent of K1 minus K2 times time equals just K1 over K2. And then finally, if we simply solve for time where B is maximized, right? That's the thing that we were looking for, just equals 1 over K1 minus K2 times the natural log of K1 over K2, right? And that's me really just solving for time here, okay? And from here, right, we could actually plug in the numbers that we have in this problem. And so in our problem, K1 is 0.06 inverse minutes minus 0.04 inverse minutes times the natural log of 0.06 over 0.04 inverse minutes. And we get about 20.3 minutes, where that's the time where B is maximized. And then what you could do is you could plug that in to each of the equations above, right? Or plug that number into all of our equations above. And we would find that the maximum concentration of B is 0.89 moles per liter. The concentration of A at that time is equal to 0.59, not 0.059. And the concentration of C at that time is 0.52, right? Moles per liter. And we can look and make sure that that actually matches the plots. And so here you can see in this example that the concentration of B maximizes. I mean, we can see it's about 20 minutes right now, and that the concentration is probably around 0.9, right? If we just took the peak here, came straight down, and went straight that way, right? And that matches what we might have, or what we calculated, which is really, really good. Now, from here, we might want to ask ourselves that we know A goes to B goes to C, but how can we change the relative magnitude of the reaction rate for A or for A goes to B and B goes to C, right? Where we know that if we wanted to maximize B, you want the rate of the first reaction to be higher than the rate of the second reaction, okay? So how might we do that? Well, one answer to that might be, let's change the rate constants, right? And our instinct might be that, well, let's just increase the rate constant for A, because if we wanted to look at a plot of this, right, and just kind of do this arbitrarily, right? So let's increase K1 here. Okay. Oops. Hold on, give me 1 second. So someone might say, let's increase the rate of reaction for K1. So I'll do that, right? And let's see what that does. So I'll zoom out so that way it makes a little bit more sense, right? And then let's undo that and redo that. And look, I mean, the maximum concentration of B increases. Does anybody know what the problem with this is? You know, why can't, I'll tell you, you can't just increase the rate of reaction for K1. Does anybody think they might know why? Why can't we just cherry pick one? maybe another way to ask this question is, in a real system, how would we actually manipulate K1 and K2 in a real system? Okay, so we have an equation for K1, right? That we had in lecture a couple of lectures ago, right? So K1, or any of the Ks, is equal to Ki0 times the exponent of minus EA1 or EAI over RT. So if we think about this, right, if this was a reaction rate constant, in a real system, how would we manipulate a reaction rate constant?
Changing
Increase the energy of the system.
Okay, so you could possibly change the activation energy by applying a catalyst or something like that. But right now, if we're doing just homogeneous reactions in either the liquid or the gas phase, let's say that a catalyst is not yet an option, right? Maybe we can do that later on in the semester. What else could you change?
Temperature.
Yeah, you could change the temperature. And if we change the temperature, remember, if K1 is equal to, K10 times the exponent of minus EA1 over RT, well, K2 is also a function of temperature. Okay. And if we change one, we automatically change the other one. Now, the question here is by how much? Well, if we wanted to calculate K2 over K1, well, that would be, K20 times the exponent of minus EA2 over RT divided by K10 times the exponent of minus EA1 over RT. And if we simplified that, the ratio between K1 and K2 would just be K20 over K10 times the exponent of EA1 minus EA2 over RT, right? And so we can change the reactor temperature, but should the temperature go up? Should the temperature go down? It depends. It depends on the relationship between the two activation energies. And I'm going to come back to that point in a second. But the thing that I want to show you is that when we do something like increase the rate constant for one of these, so let's say we increase the temperature. Well, we know that the reaction rate constant will go up when we increase the temperature. So instead of doing just this, right, where we went from the K1 that I suggested before, well, now this is also going to go up. Right? And so now one of the things that we've done is that the maximum concentration of B actually hasn't been affected that much, at least in this example. One of the things that we could have done, depending on the relationship of the activation energies, is if we go the wrong way, the reaction rate constant for 2 might actually end up being higher than the reaction rate constant for 1. So increasing the temperature in that case may actually lead us down the wrong pathway. The reactor would have to operate for a shorter time, but the maximum concentration of B would go down. And if we're really trying to maximize the yield of B, this is a problem. And so while I brought up that new term that we haven't talked about before, maybe let's talk about yield, and then we're going to come back and revisit this concept of the activation energies. Now, there are 2 types of yield, and yield really deals with you know, how much of the desired product have we made, or do we have, or are we making? I don't know if that makes sense, but how much of the desired product are we making? Or do we have now? Okay, in the reactor. And because it's trying to typically ask those two different questions, there are two different definitions for yield. So the first one is called the instantaneous yield. And that is simply given the symbol capital Y I. Okay. And you know, YI, or product I here, is the product of interest. And in this case, that's B. Okay. And the instantaneous yield is simply defined as the rate of reaction of the product of interest right now divided by the rate of reaction of the reactant, the primary reactant, which of course in this case is A. So in our example, right, the instantaneous yield, YB, would be equal to RB over minus RA. Well, we know the rate of reaction for B, right? That's the rate law, which we derived earlier. So this is just K1 CA minus K2 times CB divided by the rate law for A, which, or minus the rate law for A, which is K1 times CA. So that equals then just 1 minus K2 CB over K1 times CA. Or oftentimes I like to write this as breaking up those two things. So K2 over K1 times CB over CA. And I write them that way because you can control these differently, right? You could add excess, you know, if you wanted for some reason if you wanted the yield to go up, you always could add more A, for example. Or if you wanted to change the rate constants, you could manipulate the temperature, just like we talked about a minute ago. Okay, so the instantaneous yield of B for this specific reaction is 1 minus K2 over K1 times CB over CA. Now that just tells you what's going on right at this moment. In a batch reactor, though, that might not be the best figure of merit. Maybe in a flow reactor, that will be fine. And we'll revisit yield when we talk about flow reactors later. In a batch reactor, we're trying to set it and forget it for some amount of time. And so we have this dynamic relationship between the concentrations of A, B, and C, where if we leave the reactor running too long, we'll actually yield less B over time. And because of that, we often also like to talk about, especially for batch reactors, the overall yield, which is given a very similar symbol. It's just a little squiggle over the top of the capital YI. And that is actually defined as the number of moles that you have in the reactor of the desired product over the change in the number of moles of A. And so we have a constant volume batch reactor. And so the number of moles in the reactor at any given time is the concentration of B at that time times the volume of the reactor. And then divided by the change in the number of moles in A. And of course, the change in the number of moles is just the initial concentration minus the concentration right now, also times the volume. And these volumes will cancel. And so in this particular problem, the overall yield would be given by the concentration of B over Ca0 minus Ca, okay? And knowing this, we can actually plot both the instantaneous yield and the overall yield as a function of time, because we have equations that already tell us Ca and Cb as a function of time. So for our example, so here's the instantaneous yield. And that's just, like I said, 1 minus K2 over K1 times Cb over Ca. And the instantaneous yield goes down in this case because the rates of the two reactions go down, right? We're going to consume A all through the process, and we're going to consume B all through the process. So at the end, we're going to have a very, very low value for the instantaneous yield. And I know it going to negative numbers might seem kind of weird, but all that's really telling us is that the reactor is operating at a point that we probably don't want it to. And an instantaneous yield greater than 0 is desirable. And in fact, an instantaneous yield equal to 0 is the exact same time where Cb is maximized. So oftentimes this is also done where you just plot the instantaneous yield, find where it's equal to 0, choose that as your operating point, okay? Now, our overall yield is extremely high at the beginning because everything that we have formed in the reactor has become B, but B hasn't had any time to react yet. So basically all the A has become B. It's only after the concentration of B increases with time that you have that second reaction that occurs. So you'll notice here that, you know, we're not trying to maximize the overall yield, right? We're going to operate at the maximum concentration of B, and the yield that we're going to realize, or the overall yield that we're going to realize, is right about 0.6, 0.65. And one of the things that we often want to do in a reactor is think about, well, how in the world can we then increase our yield, right? So how can we move this point here, or this 0 point where we maximize the concentration of B, such that the actual yield is higher? And that is a really good question. And it goes back to the same thing that we were talking about just a minute ago with the activation energies, because we had our optimum yield where YB was equal to 0, right? So this is the thing that, so our optimum yield, which is when we maximize the concentration of B, occurs, right, where that is equal to 0. And of course, we have a relationship for this, right? It's 1 minus K2 over K1 times Cb over Ca. So to increase, or maybe another way to write this, right? Since this is equal to 0, I can move this over to that side of the equation and solve that Cb over Ca, which is really the thing that we care about, just equals K1 over K2. So to increase the concentration of B, I want to increase K1 over K2. Or we had a relationship already, right? Or we can think about it as decreasing K2 over K1. We already derived a relationship for this, right? K2 over K1 was equal to K20 over K10 times the exponent of the activation energy for the first reaction minus the activation energy for the second reaction divided by RT. And here's the strategy that we can use, right? So if EA1 is greater than EA2, right? Now we have to think about, if this is the case, how do we maximize K2 over K1? Well, if EA1 is greater than EA2, this is a positive number. So to increase this ratio, we have to reduce the denominator in the exponent, right? So if EA1 is greater than EA2, we want to reduce the temperature, okay? Now, something to think about here is that that can work, but it comes at the expense of the overall rate of the reaction. And that can increase the reaction time. So I'll give you an example of that if we go back to our Excel file. So here we have K1 and K2 from the problem statement, 0.6 and 0.4. So in a case where the activation energy of 1 and 2 or is greater than 2, and we reduce the temperature, both of these would go down, right? If we decided to reduce the temperature. And if we reduce the temperature here, right, that becomes, let's say that one would become 0.05, and this one would become 0.025, okay? Let's just say. All right. And now if we look at what happened here, the overall concentration of B is actually higher than it was before. Remember, the max concentration was about 0.89. Well, now the maximum concentration is over 1, and we're going to let the reactor run then until CB is maximized. So that's about 30 minutes. And in the plot on the right-hand side here of the overall yield, at 30 minutes, the yield is about 0.7, where remember in the previous example we had, it was about 0.6. So in this case, we were able to increase the maximum concentration of B and the overall yield when the activation energy for E1 or for reaction 1 was greater than reaction 2. Conversely, if the activation energy for reaction 1 is less than the activation energy for reaction 2, we have to take the opposite approach, because then this is a negative number. So to make this number bigger, we have to make the exponent smaller, right? So to do that, we would increase the temperature, right? So increase the temperature. And in that example, what would happen is that we would have to increase the reaction rate for both of them. And just as an example for maybe how we could do that is that this reaction rate, let's say, would become 0.09, and then this one would become 0.045, right? So then reaction 1 would increase more than reaction 2. And we have a very similar effect here, where, again, the concentration of B has now gone up. Now the reactor operating time is actually lower because the overall rates are higher. And so we would operate this reactor at, we'll call it 15 minutes or so. And if you look on the right-hand side, 15 minutes is also about here. Again, we're operating at an overall yield of about 0.7 to 0.75. So the thing that we've tried to do in our lecture today is take a very classical problem where you have a reaction that you're interested in and that you want to happen, then followed by a reaction that you don't want to happen. And we derived some equations for these two irreversible reactions. But hopefully on top of that, we've gotten a couple other things across. One is the concept of trying to maximize the reaction that you're interested in by controlling certain operating conditions inside a reactor, whether that's the concentrations directly or things like the operating temperature. And also we've tried to introduce new concepts about yield, and hopefully as we move forward, we can use those to help us design reactors, not just batch reactors, but also as we get into CSTRs and PFRs.